Scientists have caught sperm defying a major law of physics. With their whip-like tails, human sperm propel themselves through viscous fluids, seemingly in defiance of Newton's third law of motion, according to a recent study that characterizes the motion of the sex cells and single-celled algae. Kenta Ishimoto, a mathematical scientist at Kyoto University, and colleagues investigated these non-reciprocal interactions in sperm and other microscopic biological swimmers to find out how they slither through substances that should, in theory, resist their movement. When Newton convinced his now famed laws of motion in 1686, he sought to explain the relationship between a physical object and the forces acting upon it with a few neat principles that, it turns out, don't necessarily apply to microscopic cells wriggling through sticky fluids. Newton's third law can be summed up as, for every action there is an equal and opposite reaction. It signifies a particular symmetry in nature where opposing forces act against each other. In the simplest example, two equal-sized marbles colliding as they roll along the ground will transfer their force and rebound based on this law. However, nature is chaotic and not all physical systems are bound by these symmetries. So-called non-reciprocal interactions show up in unruly systems made up of flocking birds, particular particles in fluids, and swimming sperm. Those motile agents move in ways that display asymmetric interactions with the animals behind them or the fluid that surrounds them, forming a loophole for equal and opposing forces to skirt Newton's third law. Because birds and cells generate their own energy, which get added to the system, which with each flap of their wings or whip of their tails, the system is thrust far from equilibrium and the same rules don't apply. In their study published in October, Ishimoto and colleagues analyzed experimental data on human sperm and also modeled the motion of green algae, Chlamydomonas. Both swim using thin, bended flagella that protrude from the cell body and change shape or deform to drive the cells forward. Highly viscous fluids would typically dissipate a flagellum's energy, preventing a sperm or single-celled algae from moving much at all. And yet somehow the elastic flagella can propel these cells along without provoking a response from their surroundings. The researchers found that sperm tails and algae flagella have an odd elasticity which allows them flexible appendages to whip around about without losing much energy in the surrounding fluid. But this property of odd elasticity did not fully explain the propulsion from the flagella's wave-like motion. So from their modeling studies, the researchers also derived a new term, an odd elastic modulus, to describe the internal mechanics of flagella. From solvable simple models to biological flagellar waveforms for Chlamydomonas and sperm cells, we studied the odd bending modulus to decipher the non-local, non-reciprocal inner interactions within the material, the researchers concluded. The findings could help in the design of small self-assembling robots that mimic living materials, while the modeling methods could be used to better understand the underlying principles of collective behavior, the team said. The study was published in PRX Life. An earlier version of this article was published October 2023, and this is on Science Alert by Claire Watson. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.